TCP/IP Fundamentals Part 1. In this video, I'll talk about TCP/IP fundamentals. You know, TCP/IP is a standard protocol used for network communication in almost all types of network. And we are going to talk about how OSI and TCP/IP is related to each other. We then look at the two-address concept. So we look at why we need two addresses, that is MAC address and IP address, for every packets that we send and receive. We'll also look at the IP address format, what IP address is designed to do, and its components. We then look at the default IP address classes, like Class A, Class B, and Class C. And then finally, difference between public and private addresses. So in one of the earlier video, we talked about OSI model in detail. Now, how that relate to TCP/IP model? Well, OSI model was actually a competing model for TCP/IP model back in 1970s. And TCP/IP model won over OSI model. This is because in OSI model, the addressing was too complex as they were in hexadecimal, whereas in TCP/IP model, it was too simple back then. So for a very long time, TCP/IP version 4 was used. As the time went by, network and internet grew. We ran out of IPv4 addresses. Now we have IPv6 address to suffice the need. Today, TCP/IP model, the one on the right side, is used for almost all kind of network communication. The top layer of the TCP/IP model, which is application layer, represents the top three layers of OSI model, which are application, presentation, and session layer. This is because all three layers are related to application. They don't ever come out of the operating system. So the network devices like routers or switches are not aware of these layers. So that's why we only have one layer called application layer in the TCP/IP model. Transport layer stayed in both models. Network layer in OSI model became internet layer. Data link layer and physical layers in OSI model were boiled down to one layer called network access layer in the TCP/IP model. But even today, OSI model is still used to describe the network communication. So we need to understand the TCP/IP protocol. TCP/IP protocol is not just one protocol, but it is a suite of protocols that makes the network communication happen. In the network layer of the OSI model, or in the internet layer of the TCP/IP model, we have IP layer, which is responsible for addressing packets to help them to get from their source to destination. At the transport layer, we have two different types of transmitting the data. TCP is the reliable way of transmitting data, whereas UDP is unreliable way of transmitting the data. In the application layer of TCP/IP model, you have different protocols that makes up the application. Things such as Telnet, FTP, SMTP, DNS, RIP, and SNMP. These are the protocols that start the whole network communication process. So let us look at the format of an IP address. So IP is one of the component of TCP/IP protocol. First thing, IP address is 4 numbers, usually called as octets. So in an IPv4 address, you have 4 octets, each number from 0 to 255. So in this example, you have 4 octets. So 172 is the first octet, 30 is the second octet, 5 is the third octet, and 82 is the fourth octet. If each octet can have a number from 0 to 255, then we're going to have a lot of IPv4 address combinations. Though it is a lot of IP addresses, the interesting thing is that we are running out of IPv4 address. So that's why the networking world came up with IPv6 address. We'll discuss about IPv6 address in future lessons. Now, when you're talking about an IP address, it is always combined with the subnet mask and typically combined with the default gateway. So you can see here I have an IP address right here, 172.30.5.82, and I have a subnet mask 255.255.255.0 and a default gateway which is 172.30.5.1. The subnet mask dictates what portion of the IP address represents the network and the hosts. So I draw a line here. Now in the subnet mask, 255.255.255 represents the network and 0 represents the host. Look at the below example. We have two computers, one with 172.30.5.82, another one with 172.30.5.83. Now looking at their subnet mask, they both have same subnet mask. So the first three octets have same numbers, which is 255.255.255. So this means they belong to same network. This also means that they can communicate with each other with no problem. It also means that they don't have to go to the router to communicate with each other. They can use their switches to communicate with each other as they are on the same network. Now the host portion identifies who you are on the network. So in the below example, the computer on the left side is host 82 and the computer on the right side is host 83. When it comes to the IP addresses, if your network devices are connected to the same switch or hub, it means that they are on the same network for the most part. But let's just say that I want to change the IP address of the computer on the right side. Let's say I'll change the IP address from 172.30.5.83 to 172.31.5.83. If we do that, then the computer on the left side will not be able to communicate with the computer on the right side because they are now not on the same network. They are on the different network. Now let's talk about why we need two address concept. This is something that we talked about in brief in the OSI model lesson, but in this lesson we are going to talk about this in detail. Let's say you have a home network on the left side, and at the edge of your home network you have a router, and your router connects to internet. Inside your home network you have two computers. One is 10.1.1.10. Another computer is 10.1.1.11. In this example, let us make an assumption that we are using a subnet mask of 255.255.255.0. What that means, the first three octets represents the network ID and the last octet represent the host ID. So in this example, my two computers in my home network can be called as host 10 and host 11. Let's say you want to share some files from 10.1.1.10 to 10.1.1.11. Now behind the scene, this computer compares its address, that is computer with 10.1.1.10 compares its IP address with the computer 10.1.1.11. They do that by comparing their subnet mask. Since both have same subnet mask, they assume that they are on the same network. If they are on the same network, computer 10.1.1.10 will start sending ARP packets. So what are ARP packets? ARP packets are broadcast messages, meaning every single computer inside your home network can listen to this ARP message. So if the computer 10.1.1.10 sends an ARP packet, every computers or every device, every network devices in your home network can listen to that ARP message. So when 10.1.1.10 wants to communicate with 10.1.1.11, it will send a ARP message to your network saying who is 10.1.1.11. So every network devices in your home network gets that message, and the computer which is 10.1.1.11 receives the message, and it will respond back to the ARP message with its MAC address. It'll say that 10.1.1.11 is me, and this is my MAC address. Then 10.1.1.10 will start sending the data to the MAC address of the computer 10.1.1.11. So you may wonder why the computers are speaking using the MAC addresses. This is because computers never speak directly using IP address. They only speak to layer 2, which is MAC addresses. When the file copy starts, it will start from the MAC address of the computer 10.1.1.10 to the MAC address of the computer 10.1.1.11. So this is how local network communication works. Now let me explain how network communication happens externally. For example, let's say 10.1.1.10 wants to communicate with computer 10.5.5.100, which is on the other network. In this case, you can see that the computer 10.5.5.100 is a couple of routers away on a different network. So once we leave your home network, you are moving into a new network which is 10.2.2. network. Once you leave that network, you are moving into another new network which is 10.3.3 network, and then to 10.4.4 network, and to 10.5.5 network. So anywhere you see a router in the picture, it is like a dividing line between your networks. So the routers represent multiple networks. Every interface of your router represents a single network. You can never have two interfaces of the same router plugged into the same network. So in this picture you can see every router has two interfaces. For this router, 10.1.1 is the interface which is connected to this network, and 10.2.2 is the interface that is connected to another network. Let's say 10.1.1.10 wants to copy the file to 10.5.5.100. The computer 10.1.1.10 immediately compares its IP address with 10.5.5.100. Looking at the network ID, they immediately know that they are not on the same network, so they'll not use our protocol to send the broadcast message to 10.5.5 network. And by the way, your router, it stops broadcast messages being sent to another network, because if the routers, if they start sending or receiving the broadcast messages, the whole network, meaning the whole internet world, will be flooded with ARP packets. So because in a local network there will be too many ARP packets sent and received in fraction of seconds. So you might be wondering how it's going to send the packets from 10.1.1.10 to 10.5.5.100. So if a default gateway is configured for 10.1.1.10, the computer 10.1.1.10 will send an ARP message for the MAC address of 10.1.1.1, which is the router IP of this network. Now the computer 10.1.1.10 knows that the computer 10.5.5.100 is not on the local network. So it will ARP for the MAC address of the default gateway. So 10.1.1.10 will say who out there is 10.1.1. Now it is not looking for the MAC address of 10.5.5.100, but it is now looking for the MAC address of the default gateway, which is 10.1.1.1. So the default gateway, it will receive the ARP message and it will respond back to the ARP message with its MAC address. So the data starts flowing from 10.1.1.10, which is the source IP address, and the destination IP address is the computer, which is 10.5.5.100. Now the source MAC address would be the computer 10.1.1.10 because it is the computer which is initiating file copy. The destination MAC address would be the MAC address of the default gateway, which is 10.1.1.1. So when the packet is sent, it will be received by 10.1.1.1 router. When the router 10.1.1.1 looks at the packet, it will understand that the client computer is trying to communicate to it, but when it looks at the destination IP, the router understands that the computer 10.1.1.10 is trying to communicate to the computer 10.5.5.100 and not with it. So the router 10.1.1.1 will send that packet to router 10.2.2.2 using its another interface, which is 10.2.2.1, to see if they know anything about the network 10.5.5. Now when the packet is sent to router 10.2.2.2, it will replace both the source and destination MAC address with new source MAC address of router 10.2.2.1 and the destination MAC address of router 10.2.2.2, but the source and destination IP addresses will not change. Likewise, when the router 10.2.2.2 looks at the packet, it will understand that the computer 10.5.5.100 is not in its network, so the router 10.2.2.2 will send that packet to router 10.3.3.2 using its another interface 10.3.3.1 to see if it knows 10.5.5 network. Now when the packet is sent to router 10.3.3.2, it will replace both source and destination MAC address with the new source MAC address of 10.3.3.1 and the destination MAC address 10.3.3.2, and the same process follows until it reaches the network 10.5.5 and its destination 10.5.5.100. So finally the router 10.5.5.1 receives the packet and it will understand that the destination IP is 10.5.5.100. So the source address becomes the MAC address of this router, which is 10.5.5.1, and the destination MAC address would be the MAC address of 10.5.5.100. So when the computer 10.5.5.100 receives the packet, it will understand that the computer 10.1.1.10 is trying to communicate with it. So to reply back, this computer 10.5.5.100 will follow the same exact path in reverse order to communicate with the computer 10.1.1.10. So this is how network communication happens, and this is the two address concept. One thing that you have to remember, the IP address, the source and the destination IP address will never change. So let's talk about default address classes. When TCP/IP was designed, it was designed to use three classable addressing in our networks today. They are Class A, Class B, and Class C. So for Class A, the subnet mask is 255.0.0.0. The first octet of the IP address would be in the range of 1 to 126. And if I take an example of Class A IP address 10.5.1.1 and the subnet mask of 255.0.0.0, the number 10 in the IP address is the network ID, which is the first octet. And 5.1.1 is the host ID, which are the last 3 octets. If I take another IP of Class A, let's say 10.90.20.11, and the subnet mask of 255.0.0.0, it is on the same network as 10.5.1.1 because the network ID is same for both IPs, which is 10. This means with Class A, I can have 16,777,214 hosts available in the network. But Cisco recommends that you don't go beyond 500 hosts per network, because if you go beyond that, the broadcast messages will be flooding the network and affecting the performance of your network. But if you would like to have more than 500 hosts in one network, then you need to start subnetting the network, which we'll talk about in future lessons. Now for Class B, it has a subnet mask of 255.255.0.0. The first octet of IP address can be in a range of 128 to 191. For example, in the Class B IP address 150.51.233.1, 150.51 represents the network ID. 233.1 represents the host ID. This means we can have 65,536 hosts in one network of Class B range. Again, you may need to do subnetting to use them because it is exceeding Cisco's recommendation of not having more than 500 hosts in one network. Now looking at the Class C, it has a subnet mask of 255.255.255.0. The first octet of the IP address can be in a range of 192 to 223. For example, in the Class C IP address 220.1.50.63, 220.1.50 represents the network ID and 63 represents the host ID. This means we can have 254 hosts in one network of Class C range. Another thing, any IP address that starts with 127 is a loopback IP address, and it is reserved for the loopback address of the local computer. Any IP address that starts with 169.254 is a PIPA address, which is automatic private IP address. You get this address when your DHCP server doesn't assign a DHCP IP to your computer. Now let's talk about the differences between public versus private addresses. Public addresses are the addresses that can be used on the internet and on internal networks. It means if I want to access a network device like a web server, then that web server needs to have a public IP address assigned to it. To get a public IP address, you need to get it from your ISP. Now, private addresses are the addresses that can only be used in internal networks, meaning the network devices with private addresses can only communicate within themselves directly, but they cannot communicate directly to the devices out on the internet. Many organizations, they will be using private IP addresses for their internal network, and to provide access to the internet, they would buy a public IP and NAT it internally, meaning share the internet to its internal network. So there are 3 ranges of private IP addresses. The first one is Class A from 10.0.0.0 to 10.255.255.255. The next one is Class B, and it can have a range from 172.16.0.0 to 172.31.255.255. 192.168.255. Finally, we have Class C, and its IP range starts from 192.168.0.0 to 192.168.255.255. Alright, in the first part we looked at the relationship between TCP/IP and OSI model, and we also understood the two-address concept, and we also went in detail about the IP address format, and we talked about default IP address classes and the difference between public and private addresses. Thanks for watching this video. For more videos, please subscribe to my channel.